We're now going to take a closer look at our underdamped second order systems. And the reason we want to do that is it turns out that underdamped response is a common model for real physical problems. So what we want to do here is we want to be able to characterize the performance in a little more detail. So in order to do that, we're going to look at our step response. And so of course our step response means we're going to have a unit step input. And the reason we want to do that is that's just going to be relatively simple mathematically. So step input, and then of course we can sort of scale that up or relate that to more complicated systems by keeping things general. So for an underdamped network, which is what we're considering, we would then have in our frequency domain, C of S, which is our output, is equal to our input. So from our unit step, we get 1 over S multiplied by our transfer function. And so as we had developed in previous videos, our transfer function in the denominator we have S squared plus 2 zeta omega n S plus omega n squared. And in the numerator we have omega n squared. So this is for our unity gain system. Now because we're considering our underdamped response, we can set some limits on our damping ratio zeta. We can say that that is between 0 and 1. Okay, so now that we have our output C of S in the frequency domain, if we want to talk about our time response, we need to transform that back to the time domain. So we can use partial fraction expansion, and we can expand that, and then once we have that, we can do inverse Laplace transform. We're not going to go through the details of that, but if we do that, what we get is we get our C of t. So C of t is our time domain output, and so it turns out that that is equal to 1 minus 1 divided by square root of 1 minus zeta squared times the exponential e to the minus zeta omega sub n t, all of that times cosine of omega sub n square root of 1 minus zeta squared times t minus phi. And then our phi is defined as the inverse tangent of zeta divided by that square root of 1 minus zeta squared term. Okay, so that's kind of a big mess. Fortunately, we're not going to be using this equation directly too much, but we are going to use it as we derive some of our important equations in the following videos. So to be consistent with the notes I have on Canvas, I'm going to label this as equation 1. Okay, so let's think back to what our response looks like for our second order underdamped system. So as we've seen in a previous video, it's going to look something like this. So here we have C of t versus time, and I've indicated our final value C of S. Now for a unit step input, our final value is going to be 1, and we can see this from this equation here, that as our t is going to infinity, that term is eventually going to go away and we're going to be left with just 1. But again, in the sort of with the idea of keeping this general so we can scale it up to other inputs, we're just going to leave this as C of S so we can expand these equations that we're going to come up with. So now looking at this, we can kind of just think about several parameters that we could use to define performance. So I'm going to list them here, and then we're going to come back and define them in later videos. So the first one to talk about is our peak time. So our peak time is basically saying how much time does it take us to get to this peak here. Another important parameter is our percent overshoot. And so as the name suggests, our percent overshoot is basically saying, quantifying how much do we go over our desired final value with that first oscillation. Two other important parameters we have are our settling time. And so we've looked at that previously with our first order system, and we're going to see it's the same basic definition. And another one also talked about with our first order system is our rise time. And so we're going to take a closer look at these 4 parameters in the following videos, and then we're going to look at a couple examples of how we can utilize these to fully characterize a second order underdamped system response.